So welcome. So we're going to do this last bit of this chapter, which is IJK notation. And what we have is we have really small images on that one, really small image on that one. So I want you to imagine that we have three axes, and in physics as opposed to math, it's a bit unfortunate, but we have slightly different orientation for axes. It's the same kind of diagram, it's just fallen over on its side. So we tend to put our x-axis horizontally across the page, and we tend to always put our y-axis vertically. And then we tend to put our z-axis out of the page coming towards you. And math kind of like falls it over, I guess. They tend to do it in a slightly different orientation. It's the same figure, if you like, it's just a different orientation. So, okay, in 3 dimensions, I'd have to use x, y, z coordinates for a point, etc., etc., etc. I'd have to keep track of what was x, what was y, and what was z. And for various reasons, rather than calling it 6x, 7y, 4z, or, 6, 7, 4, you could do that. But what we prefer to do is we prefer to imagine creating a little unit vector. A unit vector is a vector which has a magnitude of 1. It is 1 unit long. Could it be 1 Newton long, or 1 meter per second long, or 1 meter per second squared long, or 1 meter long, or whatever? It's 1 unit long. And if it's on the x-axis, rather than calling it 1x, we're going to call it 1i. So we're going to call this is not 1, it's 6. We'll call that 6i. And to let people know it's a unit vector, we're not just using it as a variable, we put a little hat on it. So we're really being careful about this. And if you think about it, that is the x component of my vector. My vector, let's draw it. My vector goes, let me change colored pens just because this is a little bit of a, oh man, I'll get the hang of this. So where is my vector? My vector goes like that, and then it goes like that, and then the base goes like that. It's like a fish tank, isn't it? Like that. Then my vector goes like that. It goes from the starting point to the ending point. So there's my vector, and I'm trying to describe it using some coordinate system. Well, 6, 7, 4 tells me that address. But if it's a vector, I want it as a vector. If it's a displacement vector pointing to that address, or if it's a force vector pointing in that direction, I want it as a vector. So we use the 6 of the little x components, which is 6 i's, and then I'd like to do the j component, and there's our little unit vector in the y direction, and that's going to be 7 of those, and we add components together to get the answer. So this is going to be plus 7j. And then if we imagine we have our little unit vector in the z direction, and it's got 4 of those, 1, 2, 3, 4. So we have 4 of those plus 4k. And if it's a force vector, we'd call it newtons, and if it's a velocity vector, we'd call it meters per second, etc., etc. So in a way, this is really quite sophisticated. It's kind of nice. It means that I can specify a complicated vector in 3 dimensions using so many i's, so many j's, so many k's. And I can do math on that then, which would be very nice. Question or comment? When you say x, y, z, what do you mean? Because I think the reason for that, to be honest, I mean, they could have done x with a hat on top, y with a hat on top, z with a hat on top. And I think the problem is, what tends to happen is people get a bit lazy about the hats, as we'll see, and before you know where you are, you're getting confused between a variable x and a direction x and an axis x and a unit vector x. So I think to be safe, they just said, we're going to call it something. I mean, clearly, IJK is a weird choice. And I think clearly It's not based on any Latin or language or anything. Somebody just said, let's make it completely different so we don't get confused. I don't know that for sure, but that's my guess on it, you know. Now, is the thing. So the next thing that the school, when I was taught it, the next thing that they did was they brought a whole bunch of examples out in 2 dimensions because it's easy to draw 2 dimensions. It's hard to draw 3 dimensions. So being not the best student, I would look at it and say, I can do that using components. I don't need this IJK nonsense. We never use the K anyway. So I could just, so I ignored it. I kind of like, well, I can blow past this. And then later on, when we're doing real 3-dimensional stuff, I hadn't built the skills. So even though we are going to use 2 dimensions to illustrate things, at least at the beginning, just you got to embrace the idea that, you know, if it's in your textbook, it's there to make you more powerful. So just embrace it. It's going to make you more skillful. It's like I'm showing you a trick shot, you know. I'm showing you a dance move. I'm showing you something that's going to be, you're going to enjoy. So just embrace it and get on with it. So we can say a unit vector is a dimensionless vector having a magnitude of exactly 1. Dimensionless, that's interesting. That has dimensions because it's not a unit vector. But that is a dimensionless thing, and that's a dimensionless thing, and that's a dimensionless thing. A unit vector is used to specify the direction and has no other physical significance. It's not the size of something, unless coincidentally the size of the thing is 1, you know. And then an IJK vector uses unit vectors to specify vectors. For example, 6i plus 2j plus 3k meters per second. I express this vector in IJK. I'm sorry it's so small. And this is going to be, well, let's have a look at our x. It's going to be plus 2i. There's the x bit. And then we're going to add onto it, and I like to be a bit careful. I'm going to go add plus 4j, and then add on. And even if I don't have a k, I still like to put them in, so I know I just didn't forget it. When I was doing my national exams when I was 16, I was doing English literature, and I had this thing down. And there was a series of questions where it'd give you a quote, and then there'd be a question, quote, and a different question, quote, and a different question. And by chance, I decided what I wanted to do, and I was going to do question 1. I read the quote from question 1, and then somebody dropped something. There was like they dropped a ruler or something, and I looked away, and I looked back, and I read the prompt it's called from question 2, and I answered that. And then at the end of the test, realized that I'd answered the wrong question, so I got no points for it. So like I was in a hole. First question, the one you spend most time on, all that kind of stuff. And that's an example of, you know, stuff happens. So if you can put in safety nets so that when stuff happens, you can catch it, it's the best thing possible. So even though there is no K, I'm going to put a K in because I want to not just forget to put a K in. And that is going to be a certain value. Could be, in this case, it's going to be, oh, shame on me. I'm going to call it meters. There's no units on this. And express this one in IJK. So, all right, so this is, well, not plus 4, but minus 4 I. And then this one is still, we've got to add on to that. It's still going to be plus 2j, and added onto that 0k. And of course you can simplify it and say 2i plus 4j plus 0k. You don't have to have these parentheses, but I like to do it certainly at the beginning to make sure I'm not messing up. And this one will be minus 4i plus 2j plus 0k. So you just get the hang of things. And they're incredibly useful, as you'll see. Make life much simpler. Magnitude and direction of any old vector in IJK. Well, let's have a look. We can determine its magnitude by using Pythagoras in 3 dimensions. So we all used to c squared equals a squared plus b squared. Well, d squared, if you like, is equal to a squared plus b squared plus c squared. It's like, you know, just 3 dimensions. So if we want to find the absolute value of a, you just do the square root of these guys. And then, so that's one skill. Then the next skill is, supposing we have a vector this guy, that should be a plus, by the way. Supposing we have a vector like this, which is not a unit vector. It's clearly not, because its magnitude is 5.4 units. So it's not a unit vector. But let's say I want the unit vector in that direction, which quite often I do. It's the right direction. It's just 5.4 units too long. That's the problem. It's 5.4 units too long. So I can find the unit vector that points in this direction by writing down the, if you like, the original vector and dividing it by its own magnitude. So in this case, I'd take this 3i plus 2j minus 4k and divide it by 5.4. So that's how you find a unit vector. You find the unit vector by taking the original vector and divide that original vector by its own magnitude. And you've got a unit vector in the direction that you want. That means you can multiply that unit vector by a magnitude and it won't change the size of something. Let me give you an example of that. Later on, we're going to do the force between two masses. And I'll tell you now, the magnitude of the force is F little g is equal to big G, the big mass, the little mass over r squared. That's a magnitude. That's not got a direction at all. And what we learn to do is we learn to multiply this by a unit vector. The unit vector has a magnitude of 1, so it doesn't change the size of the effect, but it gives you the directional information. And the unit vector, in this case, will be, say, a little arrow pointing from there to there. Well, in the problem, I would give you the displacement vector between these two guys, call that r. And I would say, oh, this is equal to that times r hat, which equals big G, big M, little m over r squared, times this guy here. Oh, sorry, times, well, this guy here, the little unit vector, which is r hat. And the way I'd get that is I'd say fg is equal to big G, big M, little m over r squared. And I'd say the original vector, the displacement I got here, divided by its own magnitude. And its own magnitude we call r. So you can see how you learn to work with unit vectors, and you're going to use them throughout. We'll have an expression for the magnitude of something. We'll have another way of getting the unit vector. Okay. So that's where we're going. We can do beautiful math with these things. You want to add up three vectors, you just set up a little grid. I think layout is important. You make fewer mistakes if you do the right layout. That's a 3, that's a 2, that's a minus 1. We want to add on to that a minus 2, and add on to that a plus 4, and add on to that a 6. And then I want to find out the value of it, so I just simply say, oh, 3 added to minus 2 is plus 1, and 2, that's going to be plus 6, and this is going to be plus 5. So I would say this is 1i plus 6j plus 5k. And again, I'm not using units. I don't like not using units. So if these are meters, this would be meters. Want to subtract? Just subtract them. You want to multiply. If you're multiplying by a scalar, just multiply every bit by the scalar. So it's 3 times 3 equals 9, and 3 times 2 equals 6, and 3 times 1 equals 3. Most common mistake is people will multiply the first one, and then they'll leave the others as they are. And that, I think that's often associated with layout. They're doing too much in their head. They're not laying it out. And you want to divide, you divide every little bit by whatever you're dividing by. So that's going to be 12i over 2 is 6i, and 4j over 2 is 2j, and etc. Yeah. Notice how I've already dropped my little hats, because, it's like, life's like that. You tend to get comfortable and you leave things out. There is another thing we're going to learn, but not today. We're going to also learn you can multiply two vectors together. If I do work is a force, which is a vector, and that force has to move through a displacement, which is a vector. And trivially, you learn that work is force times displacement, so you do it with simple numbers. But then when you get three-dimensional, you've got to do a vector force times a vector displacement. You've got to learn the techniques for doing that. There's a thing called the dot product. Have you done dot product in math yet? Scalar product? Yes? No? I'll be teaching you anyway. And then the other thing is you can sometimes, if you imagine a thing called torque, which is the turning effect of a force. And there you take the vector force, which is a vector, and you multiply it by the vector, if you like, the lever arm. It's the vector going from the turning axis to where the force is applied. And there, you're still multiplying a force times a displacement, but now you've got to do it to get a different outcome, and that's going to be a cross product, a so-called vector product. And so different techniques, but they're more sophisticated. We'll get into those later. If we look at adding vectors together, we've got basically three ways. We've done it by graphically. We did one vector plus the other vector, and we got our resultant answer, and we learned how to do a vector diagram. And then we said, well, look, let's be a bit more mathematical, so let's practice breaking vectors up into components. So we had the x component for the red vector and the y component for the red vector, and then we added onto it the x component for the blue vector and the y component for the blue vector, and we could add those things arithmetically, which we're really good at because we've done it for like 15 years, and then we can basically get the x component for my answer and my y component for my answer, and if need be I can find the angle using 10 to the minus 1, and I can find my overall length using Pythagoras. So I can do that. That was great in 2 dimensions, but in 3 dimensions that would have got really messy. It would have been just awkward. And then we said, well, let's do something which will help us in 3 dimensions. And so we invented these things called unit vectors. And so we said, oh, well, basically I can break my 2 vectors up in my 2 vectors up into an I component for the red and I component for the blue, and the J component for the red and J component for the blue, and add them together. So these are kind of similar. What the difference is that this thing enables us to keep track. IJK is a great way of laying things out and labeling. This is an X bit. That's a Y bit. They're not the same. Whereas with components, because you don't usually label what the X bit is and what the Y bit is, it's easy to get them confused. And we'll see that in 2-dimensional stuff when we use components. So, can you have a go at this, please? Can you express this vector? Pick out the right answer. Hopefully there's a right answer there. Let me get my thing on. If you're not going to do it, just click away at something. Use E if you're not going to do it, so that I'm not waiting for you. And it's deceptively simple. You'll look at it and you'll go, I know how to do that. And then you'll find out that, oh man, guess what? You know, this is really valuable. It is really valuable. Give it just a few more minutes. Okay, I'm going to stop you there. Okay, stop. And we're going to see, pretty well everybody's saying C. Let's have a look and see. Where does that come from? Basically do the X bit, and the X bit is like that. And that's 4 in the X direction, which is 4I. And then we do that bit, and that is 2 in the plus Y direction, so that would be plus 2J. So that would be 4I plus 2J. There's no K. Cool. Can you do that one? So we're using a bit of trig and that. Can you express that for me, please? So we're back. Let's stop this. Let's have a look and see what people are saying. Mainly C. Let's have a look. What would I do? I would come along and I would, first of all, visualize. Where's my pen gone? Sorry about that. Let's get my pen. So first of all, I'd visualize, I'd come down here and I'd draw my x component in, and I would say that is 7 cosine 25, and then I come along here, I draw that guy in, and I go, that is 7 sine 25. They're both positive because they're in the positive directions that we typically take anyway. So then that would be, my ijk vector would be 7 cosine 25i plus 7 sine 25j. And then I can just use my calculator. And I got, what, 6.344. So this would be 6.3i. And then this would be, let me just work that out. 7 sine 25, and that would be 2.95, 2.96, so 3.0 k plus j plus 0k. And these have got dimensions on, so meters. So that would be 6.3 and plus 6.3 and plus 3, so it would be c, I guess, yeah. So it's not bad. Very nice way of bookkeeping. It's a nice way of laying things out. So you have columns and it works. And that's half the battle. Given this displacement vector, determine the magnitude of this displacement. So how are you going to do that? What's the magnitude of that, please? So we're back, and let's just stop this, and let's see what people were saying. Mainly B, and let's have a look. How did we get that? What we said was, we said that, oh, so let's just visualize a little bit. So there's my 2, there's my 4J, and there's my, so if I do my 3-dimensional stuff, what I'm doing is I'm finding the length of a vector that goes from there down to that corner. So I'm trying to find that length. Try and get away from just having numbers and try and get to visualization. It's the thing that you need that most people are not practiced in when they walk in. And I know my magnitude, let's call this R. So my magnitude of R is equal to the square root. It's going to be square root of 2 squared plus the square root of minus 4 squared, plus the square of minus 4 squared plus the 5 squared, sorry. So my R mag is going to equal, it's going to be square root of 4 plus 16 plus 25, which equals a square root of 45. And I think that works out to what, 6.7 I've calculated. So R mag is equal to 6.7 meters. So that guy, not so bad. And then given that displacement vector, determine the direction, which is, get me the unit vector of that, please. So this is going to take us a little bit longer. So we're back. Let's stop this and see what people are saying. And people are saying mainly A. So let's have a look at that. I did a quick diagram at the side trying to illustrate. So this vector here is this vector here with a little vector sign on top. And what we're trying to find is this little vector here, which points in the same direction but has a magnitude of only 1. And so we say, well, the unit vector is equal to the original vector over its own magnitude. I guess I show the magnitude like that. This is the magnitude. And this is the original vector. So if I look at this, it's going to be 4i minus 2j plus 3k. There's the original vector. And then its own magnitude, I get that by using Pythagoras, so that would be 4 squared plus minus 2 squared plus 3 squared. Mistake sometimes is people will look at that negative sign and they'll say, oh, so in the Pythagoras it's a minus the square of the next thing. When it's not, it's the sum of the squares, and this thing happens to be a negative 2. So it's not the operator that gets that. That guy there is attached to the minus 2. And that is to some extent one of the advantages in having these things in parentheses. You wouldn't make that mistake if you always wrote these things down like that. Because you'd say, there's one component, there's the other component, there's the other component. So of course I'm going to square the minus 2. Because you're adding, the process of finding the resultant vector is adding the components together. The operator is addition. We happen to sometimes have negative vectors that we're adding. And we tend to say mathematically that is equivalent to that, which it is. But to some extent, can you see how there's a little bit of the meaning is obscured by that, or can be misinterpreted? Because people say that's a negative operator, when it's actually a positive operator affected by a negative sign, if you follow me. It's a summation, but there's a negative sign there. So sometimes people will put down minus 2 squared rather than, it's always plus for Pythagoras. So this would be 4i minus 2j plus 3k over, and this would be the square root of 16, and 4 makes 20. It's the same thing, isn't it? Oh no, it's 29, isn't it? 16 and 4 makes 20, and that makes the square root of 29, which equals, and the rest is, you know, literally sums. It's, what is the square root of 29? So I can go second square root 29. That's going to be 5.3, so it's 4 divided by second answer is going to be 0.74. And it's going to be a positive. And then let's look at the next one. It's going to be 2 divided by second square root 29 is going to be 0.37. And this is going to be a, well, it's going to be a minus 0.37. So let's put that minus 0.37j plus, and that's going to be 3 divided by the square root of 29. And that's going to be 0.56, I guess it is, 56k, and that's going to be a positive. So if I write this out in the final form, 0.74i minus 0.37j plus 0.56k. It's all going to be in meters. Got to have your meters, put it in a box. So what do we have? 0.74. Is it the top one? It's the top one, isn't it? It's A. Yep. Yep. Cool. And let's do a bit of sums with it. I'll do these. So sums with this. We want to add these two guys together. Oh, we just go I, J, K. I want A, which is 3, 6, minus 2, added to B, which is 4, minus 2, and 3. And the operator is to add, so I'm going to go 7i plus 4j plus 1k. And again, I've got no units on it, which is a pity. Okay. Want to subtract? Man, this is easy. It's going to be 3, 6, minus 2. Now I'm going to subtract B, and just my own idiosyncrasy. Well, let's just do it the more common way. So 4 minus 2 plus 3, I'm going to subtract. So it's minus that. And let's have a look. 4, that's minus 1i. 6 minus minus 2 is plus 8j. Minus 2 minus 3 is minus 5k. I prefer to put it as, I prefer to do my subtraction by switching the signs on these. Let me show you. I prefer to go for the subtraction. I'll go 3, 6, minus 2. I prefer to go minus 4 plus 2 minus 3, and then just add them together. You know, A minus B is the same as A added to minus B. So I prefer to add them to, I just find it easier when I'm doing this to go, that's minus 1, and that's going to be plus 8, and that's going to be minus 5. I just find that easier. So, you know, I mean, that also works. And then you want to multiply A by 2. I'm going to say, oh, IJK. I'm going to do A by 2. I'm going to say that's going to be 6, 12 minus 4. I'm going to add on B. B is 4 minus 2, 3. And that's going to be 10I plus 10J plus 1, minus 1K. Sorry, minus 1K. And what did we just do? We took an arbitrary three-dimensional vector and we doubled it and we added onto it another arbitrary three-dimensional vector and we got our components of our answer. It's incredibly powerful. We just did manipulations in three-dimensional vectors like it was just sums. Because the IJK reduces it to sums. That's the genius of it. It makes what would be an incredibly hard thing to do, using trig or something like that, and it makes it like a walk in the park. It's just the nicest thing out. So embrace it and master it and just get all the points for it. If you can't do this, you're basically finished in physics 2. It's not going to happen. If you can do this, you get a whole bunch of points in physics. You've got to apply it to the right equation, but this is so good.